this lesson, we're going to look at the derivation of Boyle's law. And this style of derivation is going to apply to our derivations in future lessons of Charles' law and Gay-Lussac's law. So what we're looking at with Boyle's law is the relationship between pressure and volume of a gas at constant temperature. And what we want to be able to do is we want to be able to change one of those variables, either the pressure of the volume, and determine the unknown variable after the change has been made. So if I change the pressure, what's my new volume? If I change the volume, what's my new pressure? And what we have here is some data similar to what you would have collected either in an experiment or using a simulator. The pressure and the volume. Qualitatively, we can say that they are inversely proportional. So as pressure goes up, the volume goes down. That's an inverse relationship. What we'll also look at here is this last column, and I'll talk about it a little bit later, but what I'm looking at is the pressure times the volume for each of these data points. And what we can see is that it's relatively constant at this constant temperature. The next thing that you can see here is a pressure versus volume graph, so graphing that data or similar data. And then we also have beside here a pressure versus 1 over volume. And in our mathematical derivation, we'll see why we've done this. You'll see that we've got this nice linear relationship, and we'll come back to this graph to see how it's helpful. So we've got this qualitative relationship where we know that pressure and volume are inversely proportional. And we want to change that into a mathematical expression. So the mathematical expression for that is that pressure is proportional to 1 over volume. This little fish is proportional to. And anytime we want to change a proportion into an equation, what we need to do is introduce a constant. So in this case, we're going to introduce constant K. We don't need to worry too much about this constant because what you're going to see is that it ends up disappearing in our derivation here. Okay? But we'll make a connection to our graph in a moment. The key here, though, is to understand that to take a proportion and change it into an equation that's going to be useful to us, we need that constant. If I have this constant, I can solve for my unknown pressure and volume if I have one of the variables. So if we look a little bit more at this constant and go back to our graphs, what we can see here is if we look at this graph, that's a linear relationship, and I connect to y is equal to mx plus b. What I can see is that the equation of this line is actually pressure is equal to my slope. I'll call my slope k in this case, and my x variable is 1 over v. The intercept here is 0 because if I've got no pressure, then I'm going to have no volume. So what we can see here is this equation of this line, pressure is equal to the slope of my line, 1 over volume. And so from that, what we can see is that if I rearrange this, pressure times volume for my gas is always going to equal to a constant. So if I take the pressure and the volume in this gas and compare it to the pressure times the volume of this same gas, okay, where we've increased the volume, then these are both going to equal that same constant. So just like our data from above, every time I have a pressure and a volume, if the gas is held at the same temperature, P times V is going to equal a constant. And so does it mean we have to solve for the constant? No. What it means in the statement of Boyle's law is that since P1 V1 equals a constant and P2 V2 equals a constant, then we have this relationship here that P1 times V1 must equal P2 times V2. And this, like I said at the beginning, is going to be useful because if I start with a gas at a certain pressure and a volume, I can change the pressure and I'll be able to solve for my new volume. Or I can change my volume and solve for my new pressure. In this second statement of Boyle's law, instead of P1 V1 equals P2 V2, what we have is P initial, V initial is equal to P final, V final. It's just another way to write the same relationship.